Good afternoon and welcome to today's CIM webinar, Optimization in Mineral Processing, Remote Implementation During COVID-19 Times. Our panelist presenting today is Dr. Sohail Nazari, Director of Digital Transformation at ANDRITZ Automation. My name is Guylaine Richard, Professional Development Officer at CIM, and my co-organizer is Michelle Bicom, Managing Editor of the CIM magazine. On behalf of all our colleagues, we thank you for joining us. Before we get started, some housekeeping. If you're joined with your computer audio, make sure you selected the computer audio button on your control panel. And if you dialed in with a traditional phone, ensure the phone button is selected. If you have any questions during the presentation, please type them into the question box in the control panel. The questions will be held until the end for the Q&A period. And now, without further ado, we will turn over the webinar to Sohail to kick off the presentation.
Well, thank you very much, Guylaine, and thank you, CIM, for hosting this webinar. And thank you, everyone, for attending, taking it some time off from watching Tiger King or Love is Blind. We'll just keep half an hour and you can go back to that. This is interesting times, and today we're going to talk about a little bit how we can take advantage of it. And let's start with that. So who we are is ANDRITZ Automation. We are in mineral processing, basically. You might have heard us from our separation equipment, solid liquid separation equipment. And on the engineering side, we provide all the services for turnkey services in mineral processing for electrical and power engineering, automation. We are vendor neutral in that part. And then we do a lot of optimization and advanced process control. That's the part that this is our proprietary softwares and services, simulation and digital twin, and as well as asset management, improving the reliability of the plants. You also might have heard us from the Disrupt Mining competition that is hosted by Newmont Gold Corp. In 2019, we were the fortunate team to win the Disrupt Mining using our digital twin solution to actually train AI algorithms. Now, today, we are not going to talk about that part, but what we are going to talk about is about the optimization with different, using different methods. Now, let's talk about the elephant in the room. It's a COVID-19 time. We are all sitting at home, most of us. The critical personnel are working at the mill, but a lot of engineers, a lot of consultants, a lot of corporates, we are all at home, rightfully so. But there is an opportunity here, and the opportunity is the cultural shift that is happening because of this remote work. And that cultural shift is that we need to make things done remotely. This is important because maybe we all know that there is no other option. So I will come back to this later on in my presentation, that this small fact is going to change a lot of things, the way that we're going to work. And also later on, after the COVID is gone, maybe we don't go back to the same old, and maybe this is something that can stay with us. Now, today, we're going to talk about optimization on mineral processing. There are optimization is a very broad term. Basically, we are thinking of, we have process performance optimization, how to improve the throughput, how to decrease the cost. We also have the asset management and advanced monitoring for increasing the reliability or availability of the plant. And there are a lot of technologies to use and frameworks to use, like advanced process control, digital twin, data analytics, AI, and a lot more. But today, we're going to focus on one of those, improving the performance of our process and using advanced process control, and talk about remote implementation. The reason that we thought we start with this is because the technology is very proven. It's not, and the ROI and the results are very fast. And that's something in short term we thought that would be of interest of any decision maker or anybody who wants to have influence on the improvement of the plant. We want to have very short results. Okay, so by that, let's start with talking about our friends, which is the PID controller. I'm sure that most of us have heard of the proportional integrator and derivative controller. It's everywhere, and rightfully so, because it's free, and it's very easy to tune and very easy to understand and very predictive to how it behaves. So no surprises. And that's great. But the problem with the PID controllers is that on the specific processes, there are inherent limitations. So when the process is nonlinear, nonlinear process like thickener, for example, operation, it's a nonlinear process. Or when there are multivariable problems, like there are control variables that have influence on different process variables. For example, when we talk about sag mill control, we have the feed coming in, we have the water, we have the particle size distribution having effect, the speed of the sag mill have effect on the weight of the sag mill, on the throughput. And also when there are big time delays, let's go back to our example on thickener. When we change the underflow from for the thickener, when we and then we increase the flow, then the density will decrease with a time delay, same as in the sag mill feed. So when there are places like that, then we have a problem with the PID. And the problem is that when there is lag, the PID controller cannot inherently provide the optimum response. Now, I never said that we just get rid of all the PIDs and have a different solution. There are places that a PID is perfect. Like, for example, there are fast responses loop like flow control, or when they are places that regulation is not important, like when you have a buffer tank, or the places that fluctuation is not important, when you immediately take you have an analyzer for your pH and you have a mixing tank there. So where the places that fluctuation is important, that's the places, and then there's an inherent and then there's a time delays on nonlinearity, that's the places that we need to have an alternative. And that alternative is the model predictive controller. Now, the problem with the expert systems that you have heard a lot through the last 30 years is that that is available in the market is that if you still have the PID controllers that are control those specific loops that is not suitable for PID controller to control, and then you have a layer on the top which does the optimization, at the end of the day, you will end up with that fluctuation. You can't get away from it. And what happens is that that layer, the top layer for the logic, expert logics and all that, becomes more and more and more complicated because they are trying to go around the problem with the PID. And I will have examples for you later on. So what are we proposing here is to actually have a very hybrid approach. So let's stabilize with a multivariable model predictive controller that is in a specific areas that is required, and then have the optimization layer on the top that can work with that model predictive controller. And obviously, what we are providing in ANDRITZ is basically on the top of that. At the same platform, we have the digital twin and optimization on the in the plant-wide. But today, we are not going to get into that area. What we're going to focus is the each area, how can we improve the performance of, for example, sag mill or ball mill, hydrocyclone, or flotation, or thickener, or crusher. So what are we trying to achieve here? I'm sure that you have seen the graph on the left. Basically, the variability is the reason that we cannot push our process into the optimum place. Like, for example, let's thickener. On the thickener side, we have a limit, and that limit is the torque. The torque limit is, so when we have variability on the torque, we never can go higher than the limit that the torque has. And if we go higher, then we have to raise the rake. So what ends up happening is that on average, our operators will end up operating in the safe zone, which means that they will go in the lower density for the underflow, or the bed has to be, the level of the bed has to be lower. Now, if we can decrease that variability using our model predictive controller, now we have a room to push. So if I decrease the variability of the torque, now I can push the torque toward the limit and still be safe, and then now increase my density. The same logic goes into the hydrocyclone ball mill. Variability there will have a big effect on our recovery. If I have the particle size distribution that has a higher PAD, then recovery, and if I have lower PAD, I have lower recovery. So I have an optimum point, and that variability is going to hurt my recovery. Same on the sag mill. So we'll talk about that more as well. So that's the plan. Decrease the variability and push toward the optimum value. Now, to come back again, expert layers and expert logics are good, but certainly there are, and I understand that there are a lot of mills around the world that already have invested in those. It's a good investment. The problem is that there is money still on the table, and then you are able to improve a lot further if you need to, and makes things much easier as well, because then it's more understandable what the system is doing. So let's move on to practical applications and some results. So for example, on the sag mill, what are the problems? It's a multivariable problem. As I said, there's a feed, there's a speed, there's a rotation speed, there's a water addition, the particle size distribution changes, and you're trying to optimum your throughput. And you're trying to keep the weight constant at the right point that can give you the maximum throughput. Now, the problem is the variability of that weight can hurt you on the throughput, on that Powell curve. Also, the variability can make your power consumption very inefficient. So there's a lot of opportunity to improve with the sag mill, increase your throughput, decrease your energy consumption. And let's look at with the approach of the model predictive controller plus the optimization layer on the top. Like, I handpicked some of the results here for you. One of them is from, some of them are from MLP. We can show it because there are published results, but the other ones I can't provide the name. But basically, these results are the comparison between the sag mill advanced process control with the model predictive controller and the existing expert layer or expert system that was on the site. So that shows the improvement from even the existing. So the production increased by around 3% to 4% throughput, and the energy save. Now, these results are drastically much bigger if there are nothing on the site. We've seen the improvement of up to 13% increase of throughput when you run the SAG mill manually, or you run it using the PID controllers only. And that is a big improvement. So, the average that we see is around 5% to 10% improvement of the throughput when there is nothing else on the system. But if there are some expert layer there, then you can see the results of 3% to 4%, 5% improvement of throughput. Let's look at the ball mill hydrocyclone. What is the problem there? So we have the density that we want to control. We have the pressure that we want to control. You only have a limited amount of the ball mill box, and then you have a lot of, you are only able to control the feed rate to your hydrocyclone. You have the water addition. So there's a multivariable problem there. And you want to optimize your PAD, and you want to keep those density and pressure constant as much as possible. So again, that's the problem with the PID. That's where we can use our model predictive controller with optimization and also the digital twin if we want to put there. And let's look at some of the results there. So the recovery increase of between 2% to 3% is typical because of having the PAD fixed at a point that the metallurgists say that that's the optimum point. When we decrease the variability, then the metallurgists can look and see where is the best recovery. Also, there is a big energy save opportunity there as well. The last one I want to share with you is the thickener. Obviously, the flotation and other places we can do, but I thought that also go over the thickener with you. What is the problem with the thickener? We talked about this a little bit. So, for example, we have our flocculant addition, we have our underflow, we have the feed coming in, particle size distribution changing, and we have some handles, 2 or 3 handles to just control that. There is a big time delays, there is a big nonlinearity, and use the PID controller there. You end up seeing, you hear a lot of times the operators say, take it out from the auto, and you ask them why, and they say, oh, I can do a better job, or it's too slow. And then usually people might say, oh, let's tune the PID. It's not the problem of the tuning, because either you make the PID too fast, and then it becomes, so it's responsive, so it becomes much, the variability increases, or make it sluggish, and then it just defeats the purpose. So let's look at some of the results. Now, these results are not compared to the expert system. It's basically the results from the PID controller or the base level automation that is there, or manual. And we can see that we can increase the solid discharge somewhere between 3% to even 6-7%, and these are the percentage of the density. So, for example, from 52% to 55%, 3% there, like that. And we have a lot of opportunity of the flocculant save, so depending on the application, 4% to 25% there. And depending if your thickener is on the concentrate or is in the tailing, there are different strategies. So as you can see on the summary here is that we can have each area with the advanced process control, digital twin, and expect to have improvement results on the crusher, 5 to 10% increase of the throughput, power reduction on the SAG mill. We see somewhere between 1 to 13%, ball mill hydrocyclone increase of the recovery, and so on, so forth. Okay. As I promised, let's talk about implementation now. So usually these projects are around 4 to 6 weeks. And the steps of these projects is we gather information 1 week, and 3 to 4 weeks we do pre-configuration. Then we go on a site, we do 1 to 2 weeks on the site, and then 2 weeks of remote monitoring, and look at the performance and handshake and make you happy. But if you look, there is in the gathering information, 50% of that is usually done on site when we go on site for that. And then also site implementation, the 100% of that is on site. The rest we do remotely. So let's address how we can overcome those areas doing it remotely. So why do we go on site? Basically, we go on site to understand the physical reality of the meal. See, that's important because a lot of time we look at the PNID and there are sensors there. There is some circuit design, and then when you go on a site, when you start talking to people, when you start talking to the maintenance and operators, you understand it's a completely different reality. Now, if somebody tells you that by just reading the PNID, I can design everything for you and I know how your plant is working, they never set foot on a mineral processing plant. So basically we have to have that communication. We sit down and talk to the metallurgist, operation, maintenance, control, and understand what is the reality of happening. How can we overcome that? Well, we have to have then a lot of remote meetings and be aware of the reality that things that we see on the paper is not the reality that is in the plant. Also, sometimes we look at the sensors, the physical, how they're installed. So we have to ask the site personnel to go take a pictures, take a video. So that part we can overcome. Then another reason that we go is establishing personal connection with the champion on site. Now, it's important because the success of each of these projects requires a champion that actually is from the site and takes the responsibility to make everyone buy in. And that champion is usually a metallurgist. So basically, we need to establish that personal connection. Now, the good news is of the COVID, we are all learning how to establish personal connection through remotely. So that part, we need to have active communication and work. The most important part is communicating with the team when we are implementing, tuning, during the commissioning time, especially operators. Now, here's the part. When we are there, we sit down with the operators, we make sure that whatever changes we do, the operators is there and they help us and all that. That's the important part. How can we overcome that? There are different ways. One way is that to actually assign somebody to be our ear and eyes from the customer. The champion is on site to do that for us, and we are constantly talking to them. Or we can use the teleconferencing methods, for example, the hardware and software that allows us to understand what is happening in the room. We are doing some of these projects right now remotely, and there are a couple of different options that we are using right now to make it effective. Another part is training the operators, which is a big part. If the operators are not buying, if they're not trained enough, they will make the project fail. That's a reality. And we have to make sure that that training is done remotely efficiently. And being on the same time zone, that's important. And that is part that is coming from, well, if you are a global company and you have engineers and consultants around the world, then that part is not that much a big issue. But by doing a remote implementation, there will be obstacles that comes, which is like, for example, remote connection and speed of that connection. That's so important. Usually big companies nowadays, that problem is solved. They have a big IT group that allow you to do that. If that's not the case, there are solutions available like engineering in the box. We can send that establish a very secure connection, and with the satellite or other methods that can be temporarily, we can bake those remote connections. IT/OT cybersecurity obviously is very important. There are many different ways to actually address that. Like we and ANDRITZ, we actually acquired a company from Israel. It's called Ontario, which is the ex-military cybersecurity officers that they made this company, and now we are helping the customers with the cybersecurity. But many companies have their own cybersecurity, and that's not a problem, especially on the temporary basis. We can address that. also efficiency of implementing the project. That's the problem that I believe that because of the COVID, now we are changing. That's the shift of the culture that I said at the beginning that will help us to make that efficiency happen. So what we see is that remote implementation of these projects that bring a very fast return of 4 to 6 weeks return is completely possible. It requires the buy-in of you as a customer. And also, if you have some people still on the site, those are the people that we can work with them. So it is complete possible, and we are doing it right now.